Hello everyone. Welcome to our this week Rutgers Efficient AI seminar talk. And today we're glad to have the Professor Jingjin from the Computer Science Department of Rutgers University to give us this talk about the efficiently solving long horizon robotic manipulation task. He received a bachelor degree from the University of South and the Technology of China, and obtained his master and PhD degree from the University of Illinois. And before joining Rutgers, he was a postdoc researcher in MIT, and he's broadly interested in the area of the algorithmic robotics, focusing on issues related to the optimality, complexity, and the design of the efficient decision-making method. And he received the prestigious NSF Career Award and also received the Amazon Research Award. So now let's welcome Professor Yu to give us this talk.
Thank you. Yeah, I'm glad to just chat with colleague from EC. Right? Happy to visit and give a in-person talk as well. So today I will discuss these long horizon robotic manipulation tasks. But before I get there, let me first kind of give a outline of what we do in our lab. So we focus on the algorithmic study of fundamental decision-making problems in robotics. To provide a few kind of examples, right? Under the general topic of collaboration and collaborative autonomy, we have looked extensively at the problem of multi-robot path and motion planning, where we want to quickly compute high quality solutions for routing a large number of robots. Now, we've also looked at high-level decision making for multi-robot and multi-agent systems. For example, how can we, best deploy a set of, guards or agents, right, to secure a one-dimensional perimeter? Or how can we deploy a set of UV sensors, right, to best, disinfect a hospital ICU? And under the topic of manipulation, we've studied some long horizon task planning problems. For example, how can we compute a good sequence to pick and place these letters, right, in this case, so that we can solve this rearrangement problem most efficiently? And how we can reason among this very complex object interaction, right, to use the least number of push operations so that we can retrieve a target object. Now, for problems like this, we produce results of the following flavor. As it turns out, many of these problems, they are computationally intractable. Now, when that is the case, we formally prove that these problems are hard, or sometimes even harder. I mean, NP hard or even harder. Now, regardless of the difficulty, we want to be able to solve these problems as best as we can. So we set out to develop state-of-the-art algorithmic solutions for tackling these challenges. Now, these are but a few examples computed using the algorithms that we have developed. Now, along the way, we have also developed general methodologies and techniques that apply beyond the problems we set out to solve. These include dynamic programming techniques for task planning challenges in robotics, integer programming framework for path-based optimization problems that is both easy to use and can compute highly optimal solutions very quickly. We've also developed novel divide and conquer techniques for multi-robot path and motion planning problems. Now for today, I will be focusing on long horizon manipulation task planning. Now these problems include rearrangement, declutter, object retrieval, and so on. Now in a rearrangement problem, for example, right, we want to rearrange, say, a set of soda cans so they're nicely arranged. Now, why we call this long horizon? Because if we have many objects, right, we might need to carry out many of these pick and place operations, which means we have to be careful, right? If we don't plan carefully, we might end up using a lot of these operations. So the focus for today's discussion is to compute high quality plans. Now these problems find many potential applications. For example, they could enable robots to become useful personal assistant. For example, helping the elderly to retrieve objects that is otherwise difficult to retrieve, and helping clean up kids' room. And they also find industrial applications like stacking pancakes. We recently also started a NASA project that we're trying to use robots to help with disaster relief. For example, how can we remove clutter autonomously? Now, for today, I will be discussing 4 prompts. And these prompts, from rearrangement to declutter to object retrieval, they are increasing in terms of the object interaction that is involved. Now, starting from the left, on tabletop rearrangement with external buffer, as you can see here, we are trying to rearrange a set of objects. And when sometimes, right, we have to move some objects outside of the workspace. So we call this external buffers. Now for this problem, we'll show that we can use a so-called dependency graph structure to reason how to solve these problems. Now using this dependency graph structure, we were able to develop efficient algorithms that actually allows us to compute solutions for 50, 100 objects. Now, using these solutions as a proxy, we were actually able to solve problems where we don't use actually external buffers, but instead we use buffers within the same workspace. Now, as you can imagine, this is much more challenging, and we're actually able to solve these problems fairly well. So here it's trying to arrange this into a hello IGR. This is one of our recent journal submission. Now, after that, I will switch gear a little bit and move to a problem where it becomes much more challenging in the sense that now there are very strong object-object interaction. Now, in the rearrangement problem, while there are dependencies between the objects, these are, in some sense, indirect dependencies. Now, in the decluttering and retrieval tasks, the objects are actually pushing each other. So this is much more challenging. Now, for this kind of tasks, it is then natural to integrate data-driven methods for solving them. And that is exactly what we did. So for this decluttering problem, we use a decision pipeline that involves 2 neural networks. One is a grasp prediction network that allows us to predict how good we can kind of grasp a certain object. And we also have a push prediction network that tells us if we perform a certain push, what is the predicted outcome of that push. So I'll tell you more details of this, of course, a bit later. And then we look at another problem where we want to retrieve a particular target object from clutter. Now here, the difficulty is actually a bit more. This is because, right, unlike the decluttering problem, randomness in this decluttering problem actually kind of helps, right? If you push a clutter randomly, right, it is likely that you will kind of shake loose some objects that you can grasp, right? In the retrieval problem, we are actually not allowed, right? In both problems, we are not allowed to push objects out of the boundary. That means if we're not very careful, right, and we perform push, we could actually make our future actions more difficult to execute. Now, for this problem, we used a combination of multicolored tree search, which allows us to do long-term planning, and a push prediction network that guides us to do this long-term planning. We'll see more details of how this is done in just a bit. So these are the collaborators who have contributed to the papers, the works that I'll be discussing today. Let me check. Okay. Now, I'll first start with tabletop rearrangement problem. So in a tabletop rearrangement problem with overhand graphs, the allowed robotic operation is that we can pick an object, lift it up above all the other objects, move it around, and then place it down at a place where it will not collide with any other object. So this is called a pick and place. We want to use essentially the least number of pick and places to solve a given rearrangement problem. Now, again, okay, I did not say this, right? Feel free to ask questions at any point. If any of what I'm saying is not clear, right, just let me know. Now, the challenge here is that there exists some complex object dependencies. Now, starting from the initial configuration of these three soda cans, right? Now, if we make a move like this, that is, we move the Coke can out of the way of the goal positions of both the Pepsi can and the Fanta can and the Coke can itself, then this is a good move. Because then we can move the Pepsi to its goal, the Fanta to its goal, and then Coke to its goal, right? On the other hand, if we make a move like this, that is, we shift the Coke can so that the Fanta can be moved to its goal. This actually is a bad move because this does not allow the Pepsi can to be moved to its goal. Now the question is, how can we reason formally about this when there's so many of these cans lying around, right? For these three cans, of course, it's easy to make this intuitive argument, but what if there are like tens, hundreds of these objects? Now for this, we resort to the dependency graph structure. Now, a dependency graph is induced by the start and the goal configurations here. As you can see, if we want to move the Pepsi can to its goal, we must move the Coke can first somewhere else, right? Similarly, if we want to move the Coke can to its goal, we must first move the Pepsi can somewhere else. So this creates a mutual dependency between the Pepsi can and the Coke can. And this is, let me change this to a pointer, creates a cycle, cyclic dependency between the Pepsi and the Coke. And then for the Fanta can, it has a one-way dependency on the Coke because we have to move the Coke can away before we can move the Fanta to its goal. Okay. Now, with this, we can then see that resolving dependency becomes really breaking cycles in this dependency graph. Now, for the good move that we have just mentioned on the last slide, we see that as we move the Coke can away, right, we are actually breaking this cycle. So this cycle is no longer there in the updated dependency graph. For the bad move, on the other hand, as we move the Coke can here, right, we still have this mutual dependency between the Pepsi and the Coke. So the cycle is not broken. Now, I will also briefly mention here that if the items are unlabeled or partially labeled, we still have a dependency graph structure, but the graph structure will be somewhat different. I will not be discussing this much today. Now, knowing that resolving dependency becomes equivalent to breaking cycles in dependency graphs, we want to be more quantitative, right, about this. So this is the qualitative thing. Now, if we think a bit more, right, we can see that the total number of pick and places we need to do is equal to the number of objects plus the number of temporary object displacements. Now, why is that? Now, for a rearrangement task, to move an object to its goal, right, we need at least one move per object. And then for some objects, we must first displace them somewhere else, right? So the total number of pick and places would be equal to the number of objects plus the number of temporary object displacements. And then the number of temporary object displacements actually is equal to the number of vertices to be removed from the dependency graph to make it acyclic. Now, this quantity, the number of vertices to be removed to make a graph acyclic, is known as the feedback vertex set problem. And this problem is actually known 50 years ago to be NP hard. This is among one of the first 21 problems proven to be NP hard by Karp. Now, this means that computing the minimum number of pick and places for solving a tabletop rearrangement problem is also NP hard. Now, this is bad news, right? Basically, it means that we cannot hope for a very fast algorithm, right, for actually computing a solution like this quickly. Now, as it turns out, right, this feedback vertex set problem is not only hard, it's actually very, very hard. Some NP hard problems are not that difficult, right, to solve. For example, the traveling salesman problem, right? We can actually solve these kind of problems for instances with like tens of thousands of nodes, right? But for feedback vertex set problem, you cannot even solve things with like 20, 30, right, very fast. So this leads us to alternative methods. So what we did is that we used an integer linear programming model to allow us to compute the best FVS solution. And our solution can scale to about 10 objects. Now here, I want to make it clear that a plan, right, in this rearrangement problem is really an ordering of the objects or an ordering of the vertices in the graph. So if you have a sequence of the vertices, and that is a plan. Now here, we contrast the difference between an optimal solution and a greedy solution. So the optimal solution is based on the FVS set computed using our LLP model. Now the execution time for an optimal plan is about 300 seconds, where a greedy plan takes about actually 400 seconds. So this is much more efficient. Now, nevertheless, right, solving the problem for only about 10 objects is not very satisfying, right? And this leads us to finding other methods for tackling this challenge. So we tried an alternative objective this is the running buffer objective. So in solving a tabletop rearrangement problem, the number of running buffers is the maximum number of temporarily displaced objects at any given time, right? So in solving a problem, right, at any given time, maybe there are like 4 or 3, 4, 5 objects, that are displaced, right? But over the entire problem, maybe you need to displace something like 50, right? So this is the concept of running buffer. Now, we define MRB as the minimum number of running buffers for a given total instance. Now, running buffer is important on its own, right? As we can imagine, if the minimum running buffer is large, that means we need a lot of additional buffer space to be able to just solve a given problem, right? If we don't have that amount of space to hold these things, right, then we simply cannot solve a given problem. Now, as it turns out, right, if we have a minimum running buffer solution, right, this kind of solution actually also yields total small total number of pick and places, right? So that is, if at any given time, right, the number of buffers we need is small. If we add up all these things, it turns out the total number of pick and places will also be small. Now, as an example, right, for someone, if you think about it, right, if at any given time that person has a lot of shoes, right, that means probably, right, over the lifetime, this person will also have a lot of shoes, right? So this is kind of intuition. Of course, it's not always the case, but by and large. So somewhat unfortunate is that computing the minimum running buffer is also a difficult thing to do. The fortunate thing is that minimum running buffer is actually often fairly small for these random total instances. Now here we have some data that we collected, of course, using our algorithm that we developed, right? Now, even if we have something like 100 objects at very, very dense, scenarios, right? The number of running buffers are generally fairly small. In this case, we only have like 4 or 5 of these, right? So that means we can potentially design some algorithm using this observation. What we did is that we developed a dynamic programming routine, and this is assisted with a depth-first exploration heuristic to make it run even faster. I'll be very kind of hand-wavy here, right? The time will be insufficient for me to explain this in detail. Now, essentially, the running buffer being small, right, suggests that dynamic programming is applicable because we don't need to actually, do a lot of kind of we don't need to remember many states. So we can iteratively check potential solutions with MIB equals 1 and 2 and so on, and build this dynamic programming table layer by layer. Now for each number of this MRB, we can basically try all object orderings. So the DP, the role played by DP here is that, right, instead of checking all possible object sequences, right, we only need to check 2 to the n number of possible object sequences. Now, we augment the dynamic programming with a depth-first exploration technique or heuristic. The basic idea is that there are often many plans for the same number of minimum running buffers. And this leads to a fairly effective algorithm for computing MRB. So here we are showing kind of 2 examples computed by our algorithm. One is a labeled setting. Every object is distinct. So the green one, green ones are the initial configuration, right? And we move them to the green one, which is, sorry, the blue one, which is the go configuration. Right? As you can see here also that the labeled case generally is a bit more difficult to solve than the unlabeled setting. So as we addressed this tabletop rearrangement problem with external buffers efficiently, we are moving to solving the problem using internal buffers. Now, in solving practical rearrangement problems, right, we might not have external buffers to use. For example, right, if you want to ask a robot to rearrange a desk, right, the robot cannot just toss stuff elsewhere. Now, for this problem, we basically augment the DFDP algorithm with some lazy evaluation. That is, we kind of pretend this as a problem having external buffers. We then try to find some places, right, to hold the objects that we must displace on the fly based on the minimum running buffer solution. So this implicitly assumes buffer availability within the workspace. Of course, this is not always true, right? If it works, great, right? We'll have a solution. If it does not work, we kind of get a partial solution. So we might have moved a few objects, right? But then we get stuck. So in this case, we simply, call it, okay, we're done with this current run. We're going to just restart again. As it turns out, this method is quite effective in solving these sort of problems. Now we can actually compute very, very good solutions with very few number of pick and places fairly quickly, right? So here's one example where we arrange 10 objects. Our algorithm computes only using about 1 millisecond, right? Where we can compute a very good solution with 12 actions, and it can be executed in 106 seconds. And other algorithm either takes more time and more execution time, and some of the existing algorithm takes way more number of actions. So here are some additional examples that are computed using our algorithms. Now, in general, what we can observe is that the computation time is very, very small. So we can actually solve problems with 50, 100 objects with about a second, a minute or something like that, depending on, of course, the object density. So here, the objects are actually packed together very, very densely. Okay, I think I'm on time. Now, this is the, so far I have discussed object rearrangement problem. The next, I'm going to switch gear a little bit and move to the declutter and object removal problem, retrieval problem. So in working with the object rearrangement problem, the interaction between objects is kind of indirect, right? That is, if we want to move some object to its goal, we might need to move some other object away, right? So this is, in some sense, an indirect object-object interaction. In problems like declutter, which is what is shown on the right, the object-object interaction is direct. That is, if you push one object, it will directly affect the pose of other objects. So in working with dense clutter, we must deal with this more direct object interaction. So there are kind of two challenges here in comparison with the rearrangement problem. One of these challenges is that the action space here is continuous. In fact, it's uncountably infinite. So in rearrangement, right, we are making discrete choice of objects to object to manipulate. And then we may need to do a bit kind of continuous sampling to figure out where to place an object, but that's about it. Now in the decluttering, right, and object retrieval task, we need to perform these push actions. Now, every single push action, we must select within the SE2, right? That is some position and some orientation to do the push. And we also need to specify some push distance. So this itself is quite large in terms of the number of choices, right? And we also need to deal with direct object-object physical interaction with friction considerations, right? Now, as a result, optimal solution for these problems is not obvious and it's difficult to compute. So this requires then alternative algorithmic approaches. A very natural thing to do here is to integrate data-driven methods, and that's what we have attempted. So I will start with the problem of decluttering first. How we can, and illustrate how we can efficiently perform decluttering operations using push prediction. Now, decluttering itself is a very useful task with many applications, right? For example, cleaning a room or remove clutter from a disaster scene. Now, the general goal here is to remove all objects in a scene as soon as possible. The allowed actions here in our particular setting is pushing and grasping. Now, we want to minimize the total number of push and grasp. And for this, we developed a full sensing planning control pipeline where we make the following assumptions. Now, any single object can be grasped by our system. Otherwise, we cannot solve the problem, right? And then for the scene, we assume that there's a single layer of objects. This is an assumption that we made at the training time. And then objects can be reasonably segmented based on the input RGBD image. So this is kind of the assumptions that we make. We're not here trying to solve the vision problem, right? We do integrate computer vision in our solution pipeline, but we're not trying to solve like some challenging vision problem, like doing very perfect segmentation. As it turns out, we also don't need that. So the algorithm that we developed has two networks. One of them is the grasp network, where we use this to test how well can we perform grasp for the current scene. And we also have a push prediction network that is given some input image and a push direction. What would be the predicted output of that push action on that input scene? So the overall architecture of our algorithm is as follows. For a given input, we take a RGBD image from the camera on top. And for that scene, we would try to sample a bunch of push actions. So these are different directions we can potentially push, right? And then we use our push prediction network. We call this deep interaction prediction network to predict the outcome of the push actions. So for each push action, right, we would get a different outcome. And then for both the original scene and this scene after pushing, we send this to our grasp prediction network. That is, we predict how well we can perform grasp actions for these different setups, right? As you can maybe see a little bit here, right? So here we don't have many light up kind of points or pixels, right? Here we have some light up pixels like here, indicating that these are good grasp candidates. Now, once we have all these potential grasp candidates, we basically need to make a decision. Is push better than grasp currently? If it is, we'll try to execute the push so that we can get a good grasp later. If currently we already can execute very good grasp, then we simply execute grasp on this current scene, and hopefully we'll remove some object. So in this overall pipeline, DIPN provides essentially some limited functionality of a physics engine. And then the grasp network is a deep Q network. This is modified after previous work. So how do we kind of design this deep prediction network? We try to actually using existing motion prediction networks. It turns out that they are generally insufficient. As you can see here, right? Existing work generally will blur the scene, which makes it very difficult for the grasp network to figure out how to grasp anything, right? So that means we need something more crisp. That is, we must have that for a given input image, right? The output image should have each object, right, distinct from others. So how do we do this? We use a deep interaction prediction network architecture that we designed. So this is the work by my student by Chuan Huang. So this is a bit complex. I'll only kind of illustrate this very briefly. So what we do is, for a given input image, we perform some segmentation so that we get the individual objects, right? We also encode the push action, and we build then a kind of a complete graph between all these different pieces. And then we essentially want to predict the orientation and the position of all the individual pieces. And from that, we construct the predicted image based on these segmented pieces. So roughly, that's how this network works. I mean, if you want more details, you can read our papers and check our source code. Okay. And then, the grasp network itself is largely based on previous work. So I'm not going to discuss more about that here. So for performing training, we collect data mostly in simulation and also on real robot. So after sufficient amount of training, the DIPN itself was able to achieve fairly good kind of low IOU in terms of the pose error. So as you can see here, right? So the predicted pose and the ground truth is actually pretty close. So I should also mention here, right? One limitation that we have for the DIPN is that it only supports a limited number of objects. So GN itself performs very well, and it's quite sample efficient. We can only, we can use only like 500 real grasps to actually get a very good level of performance. So as a summary of the experimental outcome, right? We were able to achieve very good completion rate for a bunch of different settings, and with high level of grasp success and very good action efficiency. So here, basically, action efficiency is the number. So if we have an action efficiency like of 50, that means we need to kind of 2 tries to be able to grasp one object, right? So if we have 100 efficiency, that means every action we do will be able to grasp something. So it's of course not possible to actually get to 100% because if we need to push, right, then we cannot have 100% accuracy. So here I want to point to you that if we have objects being purely randomly, randomly kind of constructed, if the pile is constructed randomly, it turns out that very little push is actually needed. So here are some examples. On the left, we have a random pile, which is very easy to do. And in the middle, we have some hard cases where we have carefully constructed, tightly packed together scene. And we're also able to directly, take the algorithm pipeline and the trained network and apply them on novel objects that we have never seen before. So this, as you can see, also includes objects that are not in a single layer. So you can check out our GitHub source code if you're interested. You can actually take this and run some of the simulator-based examples. Okay, now after declutter, next we're going to look at object retrieval from clutter. So object retrieval, of course, is a high utility everyday task, right? Who doesn't want to have, a assistant, right, to help us fetch something, once in a while, right? Now the goal here is to efficiently retrieve a specific object. So for this work, we're trying to do this from clutter, right? In the future, over the long term, right, we want to be able to retrieve objects from clutter in a drawer, in a fridge, and so on. Now, this is more challenging than performing decluttering, right? As I already mentioned, right, in the decluttering setup, doing random stuff, right, actually kind of helps. Now here, the current action that we perform could greatly impact future outcome, right? If we're not careful, we could perform something that makes, early actions void, right, in some sense. So this is somewhat like playing chess, but with continuous actions. That is, the action space again is uncountably infinite. So inspired also by the chess playing programs like AlphaZero, right, which uses multicolored tree search and learning together, we kind of modeled our solution after that, but for a physical system. So the action space in some sense is quite different. So we used multicolored tree search and augment that with kind of data-driven method to make this tree search more efficient. So if we use only multicolored tree search, the planning time will be very, very long. On the other hand, if we use only network-based or data-driven methods, the solution quality will not be very good. As it turns out, when we combine both of these together, we achieve a very good balance between the two. We can actually solve these problems with a very good solution fairly quickly. Now, we call the method we develop multicolored tree search and learning for object retrieval, or more. So this pipeline contains a training portion, as you can expect, right, where we collect a bunch of data using multicolored tree search itself, and then we train a push prediction network based on the collected data. I'll explain a bit more just on the next slide. And then at runtime, we also run a multicolored tree search because we still want to make long-term predictions, right? And we speed up the process by using this push prediction network. So we do not perform as much exploration as we would have to do in a classical multicolored tree search. So at the training time, we first collect a bunch of data, basically for different setups, right? We use a physics simulator and we perform a multicolored tree search over these different scenes. And because in a physics simulator, it's easy to reset a scene, right? So we can kind of play with the same setup many, many times. And we can collect a bunch of data and tells us, which actions, right, will lead to kind of good eventual scene so that we can retrieve the target object. And with that data, we train a push prediction network, which basically tells us which potential push is good to execute, right? So that in fewer such pushes will eventually be able to retrieve the target object. Now, if you want to look at how we kind of encode all these things, right? You can check out our paper. It's not actually a very complex network. So in terms of the overall algorithmic flow, here's how it works at the high level. So if we start with a real scene, right? We take a picture, we see, okay, we cannot actually grasp the object in the center, this purple object. So at this point, what we do is we reconstruct the scene in our simulator. In this case, PyBullet, right? And then we perform this guided multicolored tree search. As I mentioned, right, in this guided multicolored tree search, we do not perform the exploration as we do in a standard multicolored tree search, but we use this push prediction network to help us, figure out which node we should try. And this will lead us to an action, right, which we execute on the real robot. And then we basically repeat this process a few times. So for every single action that we execute, we also need to perform this one round of guided multicolor tree search. So here are some examples, right? Just one example, right, where we show that, right, if we use only a neural network-based solution, well, we can actually compute very, very fast, but the number of actions we obtain is actually quite a lot, and the total execution time, including the planning and whatnot, is pretty long. Whereas if we use only multicolored tree search, we could compute solutions with the same number of actions, but the planning time is very long, so the overall solution time is also very long. And then if we use our Moore framework, we can get the same number of actions using faster planning time. So this will result in shorter total execution time. So here are some examples, some more data of different cases. So here we tried actually 22 different settings. Some are from the training, some are things that the algorithm has never seen before. Okay, so that concludes the technical part of my talk. I will also mention briefly some relevant industrial projects that benefited from our study of this rearrangement problem and the decluttering problem. So we jointly with my colleagues, Abdeslam Blaris and Kostas Bekris, we tackled a robust warehouse automation project where we try to kind of pack objects very tightly, right, in a box. So this, of course, is relates to object rearrangement problem. And we also attempted a metal recycling automation project with colleagues from both computer science and ME, where what we are trying to do is, right, we want to take these radiators, right, condensers. If you crush them into pieces, right, you get some pure copper pieces and some copper pieces wrapped around with some aluminum. As it turns out, these things are actually difficult to separate using existing technology. So what we did is that we built a computer vision pipeline that allows us to kind of distinguish between different types of scrap metal pieces, right? And then we can use a conveyor belt-based sorting system to actually mechanically sort these things out if we know, which one is which. And something quite interesting that we did here is that we also built within this larger system a robotic analytic subsystem that allows us to kind of prepare samples very efficiently. So every batch of these recycled material, right? You can imagine there are differences, right? That means we probably need to retrain our network to just, accommodate a given sample, given batch of material. So we have, as you can see here, right, a autonomous system that helps us to separate these, samples and separate these, samples, and then we can take a picture and then collect a lot of data very, very fast, and then update our model using the newly obtained data. Now, with that, I conclude my talk. I'd be happy to take any questions. Thank you.
Thank you, Jingjin. So very interesting talk. Any questions from the audience? You can unmute yourself to ask questions.
Hello, Professor.
With me, Professor. Sorry.
Okay.
Go ahead.
Okay. Actually, I have a question. So when performing the grasping operations, how do we move the robot arm? So do we involve any technology like the motion planning?
Yeah, so here we do not really worry too much about the motion planning. So this is, I think, I specifically did not say motion planning, right? So here our focus is more on the task planning side, right? Motion planning, of course, is important, right? But that's not, in some sense, what I try to address today, right? So we basically kind of, because this is sort of a tabletop setting, right? In general, you can assume we can go above the object, right, and go down, right? And this is actually how most industrial kind of manipulation settings, right, are, right? Does that make sense?
Oh, yes. So we can just treat the table as the different places in the table as the pixel, different pixels in the images, like, right?
Yeah, exactly, yeah. This is actually, people have studied quite extensively, this kind of stuff, yeah.
Okay, got it. Thank you.
Yeah, so it actually even works for, in some sense, if you have object, right? If you put a bunch of objects in a bin, right? This kind of method still works quite well. So there's work by, for example, Ken Goldberg at Berkeley, right? They have this DexNet, and they actually can, grasp a bunch of things in a bin fairly efficiently by just looking at mostly the 2D scene, with, of course, some depth information. Yeah.
Thank you, Professor. I learned a lot.
Excuse me, Professor, I have another question. First, thank you for your impressive talk. And robot in your slides interests me a lot. I'd like to further learn the techniques of the algorithm and the deep learning model deployment. And my question is how do you deploy your algorithm and the deep learning model? For example, deploying with OpenCV in C++ or some other critical techniques you think is more important.
Right, this is a good question, but unfortunately, I don't really have a lot of kind of experience, I would say, right? For most of what we do, right, we're interested in the algorithm design phase, right? Going in the future, as we push this to, I guess, real systems, right? We will need to deal with this, right? I think there are actually quite a lot of, I looked at the literature a little bit. There are kind of handbooks, right, telling us how to really deploy things in the real world. I think they're basically, right, what we want to do is eventually we probably want to put this on things like a embedded machine, right? So something like, how do this called, Jetson, right? So probably that's kind of a more standard thing to do, right? You probably want to make sure that your model works on these sort of smaller platforms. But usually it's not a problem, right? If you don't perform a lot of training, at runtime, usually you don't care too much about this. Yeah, so what I know is that there are existing kind of cookbooks for how to do model deployment, right? But I have not done this myself too much.
Okay, got it. Thank you, Professor.
Hi, Dr. Yu, and thanks first for your impressive presentation. I got a quite a simple question. And for the robots, how you training the robots, how you collect the training data? Thanks.
Yeah, so I mean, I guess maybe I can use one example, right? So here, let me go back a little bit. So some of the examples, some of the data are collected using the simulator, right? Like you can see here, right? But when we try to collect the real, let me see. If we want to collect the real, right? So if we want to collect real data, right? We kind of do the same thing, right? So here, in some sense, there's a little bit kind of cheating, right? Because if we assume objects are, single layer, right? And they're kind of this sort of shape. By taking this sort of 2D picture with some depth information, right? We can actually reconstruct the scene. So this allows us to, in some sense, figure out, from the scene, the actual setup of the scene, right? In terms of the poses of individual objects and what are the objects, right? And we basically, try to collect a bunch of this result, right? So let's say if I push it in some direction, what happens, right? Then I'll have some information of what is the where each object is, right? Right. So basically, it is like in simulator, right? We just need to do a bit more effort to be able to make the data usable. I don't know whether that answers your question. I'd be happy to discuss offline, right? But it's
yes, thanks, Dr. Yu. Can you answer my question, and I will be happy to contact you offline. I know this is a big topic for answer the whole question.
Yeah. So I mean, this is as you know, right? There are lots of engineering effort going into making these things work, right? It's on a high level, it's easy to say, right? But at the lower level, there are lots of additional kind of, I guess, sweat and the blood going into it, right? But mostly by the students, not me. So yeah, but yeah.
Yeah, thanks, Dr. Yu.
Sure.
Other questions from the audience? So Jingjin, actually, I have some questions. First, so right now, when you like to deploy those like this graphs network on your robot, so you physically like to connect the robot to the PC, right?
Right. So I mean, our robot is connected using over the network. But roughly, yeah, it is basically directly connected to the PC, right? So yeah, let me see. Maybe I can find. Let me see what I can find. Yeah, maybe I don't have a direct kind of view of these things here, but some of the stuff you can see. Yeah, I'm sorry, I don't have the. I cut off the part where you can see the computer screen. So
yeah, that's fine. That's fine. Yeah. Just curious about. So right now the computation is not performed locally, right? The computation, the execution of those that you train the network, that is not performed on the robot.
No, it's not on the robot, right? So I mean, that's something, of course, important, right? If we want to deploy any of these solutions, right? So eventually, you do need to perform the computation somewhere, right? So that's why it's kind of also interesting to try to make these things, in some sense more efficient and whatnot. That's what we're trying to do, right? Yeah, I think some of what you do are very useful.
Yeah. And another question is that, so So you should, in one slide, you show that there's some comparison for different approaches, the breakdown for the planning time and the execution time, right? And so typically, I think that it also depends on like the kind of the mechanical property of the robot itself, right?
Right. Yeah.
Speed of the rotation, those stuffs.
Yeah, correct. Definitely.
And so in typical case, so like for the planning time and the execution time, so typically, which part is kind of more dominant?
Right. So I mean, so in the end, right, our goal is to, so this is sort of still ongoing work, right? We are trying to essentially make the planning kind of semi-real time. By that I mean, right, if you plan within something like 3 to 5 seconds, it's kind of real time, right? For maybe not for industrial tasks, but for home automation tasks, that will be pretty sufficient, right? So we're kind of not there yet, but the goal is to eventually be able to compute high quality solutions using real time or near real time, right? So that's the goal, right? As you have observed, right? What we do strongly depend on the robot primitives that we have, right? What can we do with the grasp? What can we do with push and so on, right? So this is in some sense also kind of a co-design sort of issue, right? I mean, we don't design our own hardware, so we have to use whatever hardware we can get, right? Yeah, but we reason about some of these algorithmic side of things, right? For example, this combination of multicolored tree search and data-driven methods. I think this is something we want to keep pushing, and I think it's very promising in terms of for solving this sort of long-term, long horizon planning tasks. Yeah.
Okay, thank you very much. Any other questions from the audience? Okay, so if no more questions, so let's thank our speaker again. So thank you, Jingjin, so very wonderful talk. And also thank everyone for attending our today's seminar talk, and see you next Tuesday. Thank you. Have a wonderful day. Bye.
Bye.